So last class I said something wrong. I realized late, just after the lecture, that I said the image of a morphism, it may not take the algebraic varieties to algebraic varieties. See, for example, if you take this this map A2 to say x going xy going to xyy. What is the image? Of course, this is algebraic map because this is given by polynomials. The image of f is little complicated, right? It did not be algebraic variety because 0 is a problem. So, but we'll see later that image of a algebraic set is a constructible set. So, what is called constructible is a union of locally closed subset. So, what is a locally closed subset? So, if you so this is the theorem of Chevalley. I don't know, maybe I will do with this theorem, but I just state now Chevalley that image of a algebraic set, say constructible set. So, what is a constructible set? It is constructible set. Is union of or finite union of locally closed subset. So, locally closed subset means it is of the form U intersection Z, where U is an open subset and Z is a closed subset. So, both U and U is open in X and Z is closed in X. Finite union, yeah. Everything will be finite because we are in Zariski topology. So, F is a morphism. Morphism of algebraic varieties under an algebraic under a morphism. So this is very useful theorem. So in the sense that there are many equivalent definitions of what is called constructible set when the image is the target space is irreducible. So another definition, another equivalent saying the condition is that the image will contain a dense subset because it is union of locally closed subset. So this is but I will come to this theorem later. Let's do some more machinery we need. So let's recall the product category. I said something wrong, I think, yes, last time. So I will correct that first. And then I will go into the proof of the theorem, a proposition. So if you have xy in your, so C is a category, and you have two objects xy, then the product of xi, if exists, xy. So sometime I will denote it by pxy or some x cross y in the category C. So sometime I will write just x cross y if these are notations. If exist. This is a diagram. So that means it's an object and you have a morphism to x and y. These are called first projection and this is called second projection. This is first of all this, and it has this universal property. Whenever there exists a map T to x and T to y, say notation say phi and psi in C, whenever you have a diagram, there exists a unique morphism from T to H. This is unique from x plus y to y and x. Such that this diagram is commutative. The diagram commutes. That means P1 phi is P1 composition H and psi is P2 composition H. Right. So this is a definition of a product. Now I said something like modules, right? R modules, but that is the map is from, see, the product is tensor product, and if you have a map from that, it is the other way, right? So that's called co-product. But anyway, let's not. So this is a definition. So now the point is that in the category of affine varieties, or in the category of pre-varieties, or in the, I will define what is called variety. I have not defined so far category of what is called a variety, abstract variety. Today I will define, because for that I need product. The product exists. Category of affine varieties, category of quasi-affine varieties, category of projective varieties, category of quasi-projective varieties. In all these categories, the product exists. So that means the product is a object. I mean, where if you take quasi-affine x and y quasi-affine, then x cross y is quasi-affine. If you take x and y as affine, then the product is also affine. If you take projective, product is projective, or quasi-projective, the product is, and so far. And pre-variety also it is true. If it is a pre-variety, product you can define. So, but the basic proof is that if you first you do it for affine variety, and rest of them are like this follow up of that proof. So we will define that. So product, the dual of product is co-product. Okay. So what is co-product? Co-product is just if you change the diagram. If you reverse the diagram, that means if suppose you have a category D, and if you have say object, if you have a diagram like this, so that then you suppose A and B are two objects in D. Then the co-product of AB, if exists. So if I denote it by say C, suppose C is a co-product. If you have a map from A to B, if you have a map through in the reverse direction, and also it has that whenever you have a, if you take some another object, say E, A, B, C, say D, if you have an object like this, then you have a unique map. So these are kind of projections. So say F1, F2. These are some canonical map, and whenever you have map phi and psi, you have a unique map from C to D such that this diagram commutes. Then you call C is a co-product of A and B. Now you see that in the so product and co-product is just dual of this. You change that arrow. Right. In algebraic topology, you must have seen that homology and co-homology. So co-homology is some kind of dual of the homology. Right. The diagrams are opposite. You take the homology long exact sequence. You take the corresponding dual. So the diagram will be opposite, and then you compute the cohomology or the group kernel by image. That is the cohomology. Right, that's how you compute cohomology, and homology is the way. So this co-product and product, so this is a dual object. But in this, for example, here what I want to say that if you consider the R is a commutative ring and you consider the R module or R algebra, for example, in our case it will be R algebra. So then you have then if you take two R or K algebra, say more K algebra, K is a field. Then A tensor B over K is also a K algebra, and they have this. This is a co-product because you have this map A to B, A tensor 1. Similarly, you have B 1 tensor B. Commutative ring K algebra means commutative ring with identity, right? So then you know that if you have a bilinear map from A to C, so if you have linear maps from A to C to B to C, so then this will factor through A tensor B. So that is the universal property of tensor product, right? So co-product exists in the category of K algebra, and we will use that. We need that to prove the product exists in the category of affine varieties. Okay. So first of all, this is a remark, small remark. If product or co-product exist or co-product, okay, let's write exists, then they are unique. Okay, that means if we have another co-product, then there is the isomorphism, and the isomorphism will be also unique. So in some sense, they are canonically defined. If you have two objects, if there is a unique isomorphism, that means you really don't have to worry about the isomorphism, which isomorphism you are choosing. So that's why unique up to unique up. So unique up to unique up. Unique up to unique isomorphism. So this is the way in the tensor product also you have seen, right? So if you have this same proof. So I leave it as exercise, okay? Take it as exercise. Same proof will work. So now the proposition. X is in affine and Y is in affine or quasi-affine. Okay. open quasi-affine over K, then identifying same with so what does it mean that AN cross AM has a topology, the product topology, but I don't want that. That topology is too weak for me. I want, but I can identify as a set AN cross AM with AN plus M, and once you identify two sets, and if one has a topology, then you can induce the topology on the other set. That's what I want. So when I say identifying means that has a topology, null space, not the product topology. Product topology is weak. Because in A, you saw that A2 and A1 cross A1. A1 cross A1, there are few open sets. But in A2, you have more open sets or more closed sets. The product, identifying the product set X cross Y. So when I say the product set means that the image of X cross Y in AN plus M under the identification is quasi-affine, and the projection map makes X cross Y into product in the category quasi-affine over K. Same is for affine. So instead of quasi-affine, if you just take affine and you do it for affine. So what we will do, we will do first proof for affine, and then we will conclude. We will say that for quasi-affine is also true using it. So before affine, the simplest affine space is as I was saying in the. So just let's recall that when X equal to AN and Y is AM, then the product is nothing but AN plus M, right? So to say that it is a product, first of all, you have to say that there are two things, right? The two things. First of all, AN plus M is a affine variety, you have to say. And of course, these are morphism. P1 and P2 are morphism. These are morphism of affine varieties. And it has this the universal property that whenever you have a map from T to A, so you have a map from T to this and T to this, you want to say that there is a map from T to this, and it is unique, right? But that will follow if you just use the fact that maps of affine varieties corresponds to the category of affine varieties and category of finitely generated algebra. These are equivalent categories, right? So if you use that, then this will say that you have a map from K x1, x2, xn, and here if I write it as xn plus 1, xn plus m, and here I have 2 t, so I take OT, so I have this map. So if I call phi, if I call psi, then this is phi upper star, and this is psi upper star. Yes. So now this is P1, and this is K x1 xn plus m. These are finally generated algebra. So this co-product exists. So the projection map, this P1 and P2 are the standard projection map. That x1, x2, xn plus m. So this is the map. This sends to x1, x2, xn, and this goes to then this is a P2 upper star, the corresponding the K algebra map. Now the point is that if you have this, then there is a unique map. So call it H upper star. Now map between this, so it has diagram come. So the map between this will correspond to map between P2 an plus m. And here diagram commutes means here also diagram will commute, right? So it's obvious then. But when x equal to a n and a y equal to n. So now assume that x is closed subset, is affine. Huh? Because it's a co-product. Co-product exists in K algebra. Finally generated K algebra. Right? Co-product exists means yeah. That's why I said this. In the category of K algebra, co-product exists. The tensor product. Kx1, x2, xn tensor xn plus 1 xm is nothing. Xn plus m. Remember kx tensor ky is kxy basically. You see, the tensor product is useful. It took some time to digest what is tensor product, right? But you see that it is used everywhere. Whenever you want to enlarge your thing, product is not a good thing. Tensor product is the correct object in commutative algebra. You just can define direct sum, but direct sum it does not really have a multiplication structure. You want a commutative algebra, so that should have a multiplicative structure. The multiplication in the direct sum is not a good thing. Many things will become zero. Right? You want a multiplication of two integral domain, you want to have an integral domain. So if you just take the multiplication coordinate wise, that will not give you an integral domain. The integral domain is a good thing to have in the ring. Okay, so now let's take two varieties, affine varieties, x and y. So these are closed. So x is suppose given by v of f1, f2, fr. Y is in f1, f2, fr in k x1, x2. Let's say this is m. Right. So if you just take the product x cross y, the product set always makes sense. Because now an cross am is identified an plus m. Similarly, x cross y also you can identify with some subset of an plus m, right. So then this is nothing but point x comma y such that f vanishes on x and fi vanishes on x and gj's vanishes on y. So this is v of, I can write it as v of f1, f2, fr, g1, g2, gs. And these fi's are polynomial in k x1, x2, xm, but I can think as they are polynomial in k x1, x2, xn plus m. Yeah. So this f1, f2, fr, g1, g2, gs. So this ideal, it is in k x1, x2, xn plus m. I consider the ideal f1, f2 up to gs and take the 0 set of that. And if I take that, that is nothing but x cross y. So first claim. So to show that this is a affine variety, I have to first prove that this is irreducible. Affine, so x and y are irreducible closed subset. Affine variety means, so claim x cross y is irreducible. In n plus n, right? Huh? Induced topology, under the induced topology. Under the induced Zariski topology of n plus n. So, suppose not. Suppose not. So then x cross y you can write it as z1 union z2, where z1 and z2 are two closed subsets. Closed subsets. And z1 is not x cross y, so they are proper closed subsets. Now I define two sets, x1, it is set of all points in x such that p cross y is in z1 and x2 all those points in x such that p cross y is in z2. So now point is that I claim that x is x1 union x2. So this is A, and another claim is that x1, x2 are closed subset. So claim A so suppose it is not, again if I prove by contradiction that P belongs to say x minus x1 union x2. Then P cross y, this is nothing but P cross Y intersection Z1 union P cross Y intersection Z2. Because X cross Y is Z1 union Z2. So P cross Y, I can write it as P cross Y intersection X cross Y. But X cross Y is Z1 union. So you just now the point is that since P belongs to X minus X1 union X2, this first intersection P cross Y intersection Z1, this is a closed subset. P cross Y is a closed subset of Z1. So this is a proper closed subset of Z1. Similarly, P cross Y intersection Z2 is a proper closed subset of Z2. Right? So that will say that what? That will say that P, so I can write Y as union of two closed subsets. But Y is irreducible. So that cannot be true. So this implies, but since Y is irreducible, X is, so that cannot happen. So that means that P is, there is no P. So that means P is X1 union, X is X1 union X2. Right. Now next is that claim B, that is that X1 and X2 are closed subsets. Now when it is quasi-affine, so when XY is quasi-affine, right. So already we proved that X cross Y is a closed subset because as a product is B of F1, F2, G1, G2. So it's a algebraic set. It's irreducible. So it is affine variety. So now you prove that this is, so you consider AX inside X bar, which is in affine, right? And in Y bar you have this. So now X, so Y here. Now X cross Y, if you take, in X bar cross Y bar, and this will be in A n plus M. Now I will not go into the proof. Now since X bar cross Y bar exists, now this product X cross Y gets the quasi-affine variety structure, and then it has the following universal property. This product exists, just now we saw, and this you prove that this is, if this is open subset in X bar, Y is a open subset, so this will be open subset. See, X is quasi-affine, right? So it is open subset. So if you take the closure in A and K, then this is X is open in X bar, because after all it's a quasi-affine variety, the closed subset of a affine variety. So this is open. So this will say that this is open. So this will say that this is quasi-affine, right? So then there is nothing, really nothing to prove much, because this will have the universal property, and then from a, okay, so complete the proof. I will not do this.